Um, you can see the name of the test I'm going over here. It's test two, alt ketone carbs, fall 24. Okay. Does it show up on your end, Miranda? Okay, cool. All right. Typical test, naming structures, drawing structures. And then this here is a lot like I went over um, Monday. This is an interesting problem here. And then we have some reactions. And of course, I'll include a flow chart. Okay, so let's start here. All right, on this one, a lot of you in the last test um, missed the difference between this and this. This is benzene based. This is cyclohexane based. Now, in this case, it's a ketone. And it's cyclohexane base. So it's going to be, this is a six-membered ring.
Professor,
Yeah.
I don't know about other people, but I'm not able to see anything on the screen. It says you paused.
How did I pause it? Let me stop sharing and redo it.
When I went out of full screen, it appeared. So I don't know. It's probably just weird.
Do you see it now?
Yes, I see it.
Okay. All right. This is based on a six-membered ring, and it's a ketone, so it's going to be a with two branches. And whenever we have a functional group on a ring, that's always carbon number one. Okay, so it's basically we start off with cyclohexanone, that's for ketone. And we have 2,3-dimethylcyclohexanone. Now, what would happen if we reduce that? What will we end up with? Well, ketones that are reduced will go to a secondary alcohol. So we'd end up with that, which would be 2,3 dimethylhexanol. And of course, if we oxidize the cyclohexanol, we end up with a ketone. Okay. All right. So we've got again, a ketone down here. This is a non-cyclic one. So let's look at the backbone. We've got 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. It doesn't matter which one we take. Let's take that one. It'd be better if we numbered from here, because the functional group number would be lower. Okay, so it looks like we have a five-membered backbone ketone. So that's going to be a pentanone at position 2. And we have two methyl groups at carbons 3 and 4. So it'd be it'd be 3,4-dimethyl 2-pentanone. Okay, so we have ketone and two phenyl groups now. Remember, phenyl is going to be the um, benzene-like branch. Okay, so we need a 7-membered backbone. Carbon number 3 going to be the ketone. And on 5, 6, we have two phenyl groups. Okay, so that's 3, 4, 5. And 6. Here we have an alcohol. Alcohol's on carbon number 1. And we have two methyl branches at carbon number 2. Here we have a Here we have a 5-carbon aldehyde. And carbon number 3. Carbon number 3, we have an isopropyl. Carbon number 4, we have two methyl branches. Okay, galactose. And it's a beta, so it's going up. Fructose. Okay, and it's alpha, so the OH is going down. And of course, this is the anomeric carbon and anomeric carbon. I like to always identify those. Okay. Somehow this Okay, name the molecule above. Okay, there's a number of disaccharides you need to know. This is one of them. This happens to be maltose, but there's maltose, lactose, and sucrose. Those are the three disaccharides you need to know. Okay, so okay, so this is going to be maltose, and because the OH is going down, it's going to be alpha maltose. Okay, is it a reducing sugar? Is a hemiacetal present? If so, it is. If it's not, it's not. This is the key to reducing sugars. As hemiacetals open up to an aldehyde, which can be then oxidized. Okay, so let's look at the OCOs. Okay, we've got one here, and we have one here. So this has no, the one on the left has no OHs, so it's not a hemi. And the one on the right does have an OH, so it's a hemi, and there's an H there. So it is a, go and do the right side one. So it's an OCO. It's got an H and an OH, and that means it's a hemiacetal. The one on the left, OCO. It has an H and it has no OH. So this is an acetal. Linkage. So the answer to this is yes, because of this. Okay. The linkage is going to be an alpha 1, 4. Okay. Alpha, because the O is going down, not up. And it's on carbon number 1 attaching to carbon number 4. Alpha 1, 4. All right. What test would you use to determine this? I mean, Benedict's or Tollens? Okay, Benedict's uses copper +2, Tollens uses silver +1. And basically, the tests are chemistry-wise exactly the same. The appearance is quite different, and the performance is quite different. Benedict's is fast. Tollens is not too bad, but it's definitely not as fast as Benedict. Benedict's takes seconds. Okay, what is meant by the term reducing sugar? That is when, if sugar has a hemiacetal that opens to an aldehyde, it can be oxidized. this is the hemiacetal side here on the right. So that means that can open up to an aldehyde, and that aldehyde on the right can then be oxidized. Sometimes. Okay, now let's do the reaction for this. Okay, so I'm going to start with the maltose, and we're going to open it up. I forgot which one it was. Alpha or beta. It's alpha. Okay, so we're going to open this up now, right here at the hemiacetal. Okay, now it's opened up to the aldehyde. And we're going to add Benedict solution in a basic environment. Okay, so the aldehyde is going to be oxidized to the acid. So we're going to redraw this being oxidized. Oh. Okay, plus okay, so we have this going to that, which is being oxidized. This going to that, which is being reduced. And remember, oxidation reduction has to happen together. No exceptions. Because when the one compound being oxidized loses electrons, it has to go to the recipient compound that has to receive it. Can't have just electrons running around hither and thither. That's called beta radiation. Don't want that. Okay, so anyway, that's the actual reaction. And that's what I went over extensively Monday. Okay, so what disaccharide? Now remember, we know three disaccharides. That's glucose, galactose, fructose. The disaccharides are maltose, lactose, and sucrose. So the disaccharides, which has an alpha 1 beta 2 glycosidic linkage. Now, as soon as I say alpha and beta in the same description, that automatically means that two anomeric carbons are linked together. The only disaccharide where that occurs is sucrose. Draw the structure below. Okay, so the top part is going to be glucose. And we have fructose. So this is carbon number 1, carbon number 2. So the anomeric carbon with fructose is on carbon number 2. Backwards. That different color. And with a hexose as opposed to a pentose. Let me back up. They're both hexoses, both have 6 carbons. The top one is a uh, pyranose ring, which is 6-membered. Bottom one is a furanose ring, which is 5-membered. Okay, so this is what good old sucrose looks like. So is hemiacetal present? Well, let's look. We have OCO. There's no OH there, so that's not a hemiacetal. And here we have OCO. No OH there either at the anomeric carbon. So neither one is a hemiacetal. So the answer is no. All right. This is kind of a combination uh, uh, carbohydrate and lipid combination. So this would be the lipid piece, which is unit 3. And this would be the carb piece. Okay, so is it a reducing sugar? Well, the carb part is going to dictate that. And so let's look at OCOs. OCO. And we have no OH attached to that OCO. So answer is no hemiacetal present. And I would typically, instead of saying 3 points, I would say 2 plus 4. 6 points. 2, yes or no, and 4 points whether you answered the Y part. Okay, what's the difference between the amylpectin and amylose? The amylpectin is branched. Amylose is not branched. Okay, amylpectin is branched at Okay, so this is amylopectin. Okay, so we have okay, and this is where the difference lies. This is where the branching occurs in carbon number 6 off the main. So this here is an alpha 1,4 linkage. This is an alpha 1,4 linkage. This is an alpha 1,4 linkage. And this is not. And this here is an alpha 1,6 linkage. So basically for amylose, this top part is missing. That's the difference. Also, amylopectin is much longer than amylose. Sometimes it can be thousands of glucoses long, very large molecule. Okay, show the reaction of Benedict solution tests with beta glucose.
Sorry, can I go back to the amylopectin and amylose?
Yeah,
Um, is the difference then, or at least the answer that you were looking for and what you gave was more structural rather than like functional? Like why the different structures or like what the different structures cause or do?
well, structurally they're very different. I mean, in some ways they're very much the same, but basically the the thing that distinguishes between amylopectin and amylose is the branching.
Okay.
And it's most people say, and it's also a larger molecule. It can be, huge. And amylose is, I guess you'd say, more fragile because it's just one long, long string. So it tends to not be as long in terms of stability. So the question here focuses on structure, though.
Gotcha. Okay.
That was your question, right?
Yeah. Thank you.
Okay, so now we're gonna take beta glucose through a beta Benedict test. Let's do Tollens instead. Okay, so we need to start with beta glucose. Tollens is with silver +1, and basic environment. So what happens is it has to open first. Let me dry it opened. So it's opened up, and here's the aldehyde here. The susceptible aldehyde is going to get oxidized. And the silver goes to silver metal. So we've got reduction. Oxidation. And then the positive result is quite, silver nitrate is very colorless. So when you dump in a reducing sugar, it turns very dramatic changes. The silver metal comes out, and the silver metal starts to tarnish also fairly rapidly. So it turns kind of a grayish color. So you have a mix of this silvery, metallic silver along with this darkened fluff of tarnished silver. So it's quite a dramatic test. Takes a while though. That's the only problem, and it's expensive because it uses metallic silver. Okay, so I think that was the last page. Oh no, not
Yeah.
yet.
The difference between the Tollens and Benedict's test, at least in the oxidation of the like beta glucose, like the beta glucose is going to have the same uh, reaction, I guess.
Yeah, exactly, exactly.
Okay, cool.
The difference, there's a good question. The difference between the two is Tollens uses silver, Benedict's uses copper too.
Gotcha.
The carb itself undergoes the same oxidation in both of them.
Sweet, sweet.
Good question. All right. Let's look at this reaction here. Okay, we've got a ketone and an alcohol together. Those can react. So this would be a ketone. 1, 2, 3, 4, 5. So this would be a 2-pentanone. And it's got, so this is 2, 3, 4. Methyl 2-pentanone. And this would be 1, 2, 3. So this is going to be a propanol. Okay, and this is going to react, the propanol is going to react twice. Excuse me. So the first thing you get is a hemi ketal, since this is a keto. So this would be go to a hemi ketal, and then it would go to a ketal. Okay, so so a 5-carbon backbone. This is going to be the backbone here. And we have a 3-carbon. So this is going to be the anomeric carbon here, number 2. So this is our secondary backbones. Okay, so very straightforward ketone alcohol reaction. And because it happens twice, if we didn't have a 2 there, it would go to the ketal, hemiketal. Then we'd have to add another propanol over here to continue on to the ketal. But because we put 2 in the beginning, that automatically means it's going to go to the full ketal. Okay, so determine for the reaction above the reaction products as hemiketal ketals, acetals, ketal, aldehydes, ketones, alcohols. Okay, so we've almost already done that. This will be the, oh, actually, I think I've done everything here. Alcohol, yeah, got all the parts labeled. Okay, and this one here. For the following structures, determine whether the structure is acetal, hemiacetal, hemiketal, ketal, or nothing. Okay, well, this is a plain old aldehyde, so it would be nothing. This has got, we've got no H and no OH, so that means it is a ketal. This has got, okay, it's got a no H, an OH though. So this would mean this is a hemiketal. Where I was looking for in this one is another problem with this answer I gave, Benedict's or Collins, is you can have an anomeric carbon, but it's not a hemiacetal. So for example, if we tried to test this with Benedict's or this, it would give a negative test. So we're looking for a so this is kind of a poorly worded question. I okay, and then up here, put a large dot on the anomeric carbons. And here's our lovely flow chart. Okay, so that's going to be similar to your tests next week. In my opinion, the hardest part are going to be these Benedict's and Tollens reactions. And then learning the structures. Those are the two biggies. Naming is kind of similar to our Unit 1. Structure, same thing. But this is the part that gives students the most challenges in Unit 2 are the structures and the reactions. So any general questions about this guy? And again, the name of this test is this guy here. So here's some more. Practice tests. And if we widen the column here. There should be a way to widen this column. Let's see, it seems like. I could have sworn I remember. Maybe it's an older version of Canvas where you can widen the column so you can see the whole name. Um, well, maybe not. Anyway, here's some more practice tests if you're interested. Okay, that's what I wanted to cover today, is that practice tests. Okay, so anything else, you guys?
I think just today, it is Wednesday, right? Yeah, okay. Today for lab, we're doing the soap, right?
Yeah,
Sweet. Exciting.
yeah, it went pretty well Monday. We had some things that were missing. I had a font rundown and everything. So Monday folks are always the guinea pigs.
Yeah, I was gonna say, what do we need to bring that isn't already there? I know we did the essential oils. That should still be in our drawers.
Yeah, and that's I have some more essential oils, and you can choose between yours you made, excuse me, or the ones I provided. So it's not required that you use your citrus oil. Some of them smelled better than others. Um, so let's see, was there another question here? Okay, and then in terms of the flow chart, um, I forgot to reproduce that. So you can use your own flow chart on the test. They've changed their policy regarding copying. I have to go through the print shop now, except for some very, very small um, number of copies. So in the print shop, it works pretty well. It's just that you have to think ahead. You can't do the test the night before, like I've been known to do. You've got to think ahead. So anyway, I've already submitted the test to the print shop, so they'll be done way in advance. But yes, we can use a note card, two-sided 3x5. Um, so anyway, so use your own flow chart. I'd recommend using the Unit 2 flow chart also. I'll try to bring, I'll try to photocopy a few just in case. Yeah, did Peep say thank you yet? I will be there probably by 2:30. I can't get in there any earlier because there's another lab in there. And the teacher usually is there leaving at 2:30, so I really can't get in there earlier than that. Um, Next week, I'm going to be there by 2. And if anything, we'd start in 3:15, room 3:15. Then we could overflow into 3:16 when people start to arrive, which I'll probably do. What about both days? I didn't see that. Let me see. Yeah, the exam's on both days again, so you can come either day. Same exam. Okay, anything else? Yeah, around 40. I think there might be a little less, maybe 39. Last time I checked, it was 41, but I know one person had a drop, so I think it's at 40 now, but it could be 39. Now we started at 55, which is typical for a chemistry class. Just your 305 probably did the same thing. And this is doesn't when I was in Washington, it was the same thing. It's just historically physical sciences, physics included, typically have a high dropout rate. Now, when you get into the higher level classes, it's that's not the case at all. Like 420, the 1 year organic chemistry, uh, probably has no dropouts at all. Uh, just because the students that are in there have already had a whole year of chemistry. So the people are going to drop out have already dropped out. But the lower level ones tend to have, particularly like Chem 300, large dropout, probably 50%. My Chem A, which is equivalent to 300 up at Sierra, same thing. Typically 30% plus, depends on the year. Okay, anything else, you guys?
Not for me. I'll see you in lab.
Sounds good.